All right, so we have this function. It's a good looking function. And it's got some bounds that we'll have to account for in a second, but we're asked to find the absolute maximum for this, right, based off of those bounds. All right, so we can create the graph if we want, but we're looking at something that has ellipsoid characteristics to it. So we're kind of in decent shape there in terms of visualization, right? So what you can do is just pop both of these into Geogebra and take a quick look. And this one I don't need anymore. I just want to go in the right direction here. Okay, delete. All right, so I'll write it as z equals x squared plus 9y squared plus 8x minus 36y plus 24 x squared plus y squared equals 1. Oh, equals 1. All right. So we have this kind of intersection thing going on. I'm just going to change the color on one of them so it sort of pops out a little bit more. All right. You have an intersection. All right. And what we're looking for is any kind of absolute maximum that might exist based off of this information. All right. And so based on what you see here, it kind of looks infinite. Let's zoom out and see really what's going on. All right. So it looks like we're dealing with an elliptical cylinder and an ordinary cylinder. All right. So you can kind of get an idea just based off of the graph, really what's going on. But, you could also do the computation as well, right? So it's just a question of what technique you want to use, So it's a question of, are you going to use second derivatives test? Or are you going to use Lagrange multipliers? Like what's going on here? This one, because you have a function bounding the primary function, it seems to be a Lagrange multiplier situation. Right. So what I'm going to do is define. Well, I got f already defined, so I'm just going to write that. I'm going to rewrite it: x squared plus 9y squared plus 8x minus 36y plus 24. The bounding. That's the constraint function. I can write that as 0 equals 1 minus x squared minus y squared. And so therefore, we can call that g is equal to 1 minus x squared minus y squared. It's a perimeter function, essentially. All right. So I would need first order partial with respect to x, first order partial with respect to y. So 2x plus 8. 18y minus 36. First order partial with respect to x in the boundary function, negative 2x. With respect to y, negative 2y. So I use my Lagrange multiplier to set one equal to the other. So as a proportional relationship, 2x plus 8 is equal to lambda multiplied by negative 2x. And then 18y minus 36 is going to be equal to lambda multiplied by negative 2y. All right, so now we just go through the process of trying to kind of piece this all together. All right, so we can try to simplify, we can try to substitute. We also have this relationship between x and y that we can pop into, right? But we have at least something to kind of get the ball rolling. All right. So just looking at it, I see everything even. So I'll cross off some even numbers, I guess. So 2x, oh no, not 2x, I'm dividing it. So x plus 4 equals negative x lambda. poor quality lambda. And same idea on this side, divide everything by 2. We have 9y minus 18 is equal to negative y lambda. Right. It looks like we can go the GCF route. Yeah, so I'm gonna, well, actually, for the left one, we wouldn't really actually for either of them, we wouldn't really have to do that if we didn't want to. But because we could get lambda equal to some numerical variable quantity. We could say divide everything by negative x. You get lambda equals all this stuff. But then you kind of run into a problem, right? Because you would do the same thing on the other side, divide everything by negative y, you'd have 9y minus 18 over negative y, that's equal to lambda. We would have these two expressions that could be set equal to each other. You'd have to do some more algebra, which we can handle, but you could also try, let me just show you real quick, the GCF route, which is to say, you take this, you write it as x plus x lambda, well, I'll write it as lambda x, I already started writing that, is equal to negative 4, then factor out an x and see where that gets. All right. In this case, it's not really doing anything because you don't have the zero product property to fall back on, but you never know. So that's just a suggestion in some cases. In this case, it didn't play out, but I just wanted to make sure I reviewed that because it comes up fairly frequently. All right. But at this point, it seems like the best way to handle it would be to set these two expressions equal to one another. All right. So I'm looking at x plus 4 over negative x is equal to 9y minus 18 over negative y. And you look at it and say, well, where's this going to get us? Well, we have another equation that we can work on, right? We have a relationship between x's and y's, and that's off over here. 0 equals 1 minus x squared minus y squared. Well, it's really over here. I'm just rewriting it down here. All right. So two equations with two variables, if they're going to have, if it's going to have a solution, it's going to come from this in some way. Okay. It's just a question of whether or not you want to do the algebra to get there. All right. So in the case of the left equation, it's kind of a mess, but it's manageable. It's got x's and y's in it. If we solve for one of the variables in the second equation, substitute it into the first one, we can get the job done. Or we can go to our friend Desmos, graph them both. Let me put it back to rectangular. X plus 4 over negative x equals 9y minus 18 over negative y. All right. It's not pretty, but that's okay. You don't want to clean it up too much because then if you do, you might lose any discontinuities that occur along the way. All right. So you just kind of bear that in mind. Right. So don't, you know, like if you got the x, the negative x and negative y to cancel out of the denominator, that might be great to get the algebra done, but then you might introduce an extraneous solution. So you got to be careful about that. All right. So now what I'm going to do is graph the other one. And I'll just write it as x squared plus y squared. So this is the same as, you know, right back to where we started, x squared plus y squared is equal to 1. Right. And so what I'm looking for is intersections. Right. So I have an intersection here, if I can get there. It's being difficult because it's irrational. Right. And also I wrote it as as not a function. So I might have to solve it for y in terms of x, but we can at least use this to get an idea that there are solutions. And then what I'll do is I'll write it as y equals the square root of 1 minus x squared. Turn this one off. Duplicate. Make this one negative. Like I said, turn that off. So I have my two pieces here. I'm looking for an intersection again. It must be so ugly. Normally, if you define it as a function, it gives you a solution, a reasonable solution, but it just doesn't look like it wants to do that for us. But if you bring it in enough, you can lock on to a solution. All right, so we're looking at, it says to the nearest 10th. All right, so, and we're gonna have to figure out which one gives us the absolute max and which one gives the absolute min, but for now we'll get our solutions. All right, so x is equal to and y is equal to, let's take a look. So to the nearest 10th, we're talking negative 0.4.9. And again, this is just assuming you don't want to do the algebra, which I think is probably a fair assumption. And the other solution, 0.2. And if we're going to the nearest 10th, that would go to a negative 1. So 0.2 and negative 1. All right, so then it's a matter of just verifying which one's actually going to give you the larger solution. All right, so what I'll do is I'll rewrite this this surface function in terms of a's and b's. So I can just use sliders. So a squared plus 9b squared plus 8a minus 36b plus 24, create some sliders here. Make sure I typed it in the right way. Looks good. So I'm going to make my a value a negative 0.4. And my b value, I'm going to make that a 0.9. All right, so it's about, so f is approximately, oh, it's lowercase f. Negative 4.2. And then a 0.2 and a negative 1. And that gives us, well, that'll be the absolute max, about 70.6. Now, if it were a rectangular bounds, it would be a little bit of a different story, but because it's a function representing the constraints, it's a constraint function, there's definitely a lot more oomph to a question like this. But really kind of the moral of the story that I'm trying to get across here is that you don't have to get bogged down with the algebra. Use technology, estimation, rounding, and all that good stuff, as long as you carry out the approach, the spirit of the approach, you're fine. So that was number 6. Number 7, kind of more like a general knowledge question, right? But this is sort of like my way of kind of getting around the whole proof thing on a practice test, you know, because I don't like putting proofs on a practice test, but I do like to put ones that involve questions that involve rules. So here's one of them. Which of the following cannot be used to find the area of a parallelogram having adjacent sides of magnitude u and v separated by angle theta? All right. So parallelogram. Let's see if this actually makes a parallelogram. It kind of did, which is good. All right. So you have vectors u and v, each having their own magnitudes. All right. So we can do a couple of things when we're trying to find when we're trying to find area, but we can also not do a couple of things. So that's kind of what this is getting at here. All right. So that fourth choice, the u plus v, this is what u plus v looks like. This is u plus v. All right. What the magnitude of that would be the length of this line segment. All right. Well, that's not an area. All right. So we can eliminate one off the bat. All right. Oh, actually, which of the following cannot be used? Well, there you go. If we're trying to identify which ones could be used, then we would eliminate that one. It turns out the one you eliminate is the one you want. All right. Now, when it comes to finding, just to kind of complete the thought here, when it comes to finding the area, I'm just looking at that first choice again. That feels like there might be a typo there. Oh, no, 180, it's complementary in the second quadrant. Okay, yeah, so these are actually equivalent to one another. So that's fine, all right? It's just a question of whether, you know, like what the story is with that magnitude of u plus v, right? So the definition, magnitude of u plus, magnitude of the cross product of u plus u and v, keep repeatedly saying the wrong thing over and over again, is u times v times the sine of the angle in between, sine of theta. All right. So kind of begs the question, all right, well, now that we know that, what does that mean? Let me just get rid of this. Now, if I drop an altitude, which we would call the height, we could figure out the area of a parallelogram by multiplying the base by the height. Now the base is the magnitude of v. The height is unknown, but there is an angle theta that separates vectors u and v. All right. What I could say here is that the sine of theta is equal to the opposite over the hypotenuse, h over the magnitude of u. All right. So when I cross multiply, I get h equals the magnitude of u times the sine of theta. So that allows me to make a substitution, which in turn allows me to come up with the area of a parallelogram formula, which would be u v magnitude multiplied by the sine of theta, sine of the angle separating the two vectors. And since we know that the magnitude of u and v, the cross product of magnitude of u and v is equivalent to that, then all three of these things would be equivalent to one another, which would make this one the oddball. So that would be a way to get at that answer without knowing that u plus v represents the resulting vector. Although that's one of the first things that you should know based off of vector operations, but you know, sometimes it slips through the cracks. Right. Number 8, create or graph the parametric. That is There's no other way to say it than to say it's a gift from me to you. As long as you know how to graph parametric, you can do it one of two ways, Desmos or Geogebra. We learned how to do it in both platforms. If you think of the Bezier curves, the tech assignment B, I believe that was B, then that kind of gets you going, thinking about how you would graph parametrics in Geogebra. If not, quick Google search will get the job done there, but it's even easier in Desmos if it's in two dimensions. All you do is you put it in as an ordered pair. So t squared, comma, ln of t. Close it up. State the appropriate domain for Desmos. Now this may or may not be enough. So 0 to 1, I don't know. How about 0 to 10? How about negative 10 to 10? Now, negatives wouldn't make sense here because you're dealing with a natural log, but you can go with whatever you want. If I put a negative 10, it's just going to disregard anything that doesn't make sense. So you're fine. Just give yourself a nice wide interval to work on. All right, but this is what we're looking at. And all you would do is take that little share, copy, pop that right into Blackboard. Okay, save it. Make sure you save it. And make sure you don't try to copy paste. It really kind of, you're setting yourself up here. What people will do is they'll copy paste this and put it in there. You're just sending me to the, Desmos calculator. You're not sending me to your calculator, right? So you got to make sure you send the right thing. So, call this question 8, final exam, save it, and then create the share link and you're good to go, all right? Now it says find the slope of the tangent line when t is equal to 1 over rad 2. All right, so what I would need here is x prime, which is 2t, y prime, which is 1 over t, all right? dy dx is equal to the y prime over the x prime. So that's 1 over t divided by 2t. If you want to clean it up, put the 2t over 1, do a little key change flip, it's 1 over 2t squared. So we would want dy dx when or if or such that t is equal to 1 over the square root of 2. So 1 over 2 times 1 over rad 2 squared, which is 1 over 2 times a half, which is 1 over 1, which is 1. All right. So that's pretty not bad. All right, as questions on a Calculus 3 final exam go, that's kind of what you hope for. Take a question like this to balance out something a little crazier like the Lagrange multiplier. Right. Number 9, iterated integral that could be used to find the surface area of the portion of the function that's below that it's bounded by the given constraints. All right, so it's given us some constraints to work off of, but if we're talking about a surface area, we're going to need some partials. I'm going to write this to the 1/2 power. All right. We know what our constraints are for x and y. It might not be the worst idea in the world to have a quick look in Geogebra and see what's going on there. All right. So quick z equals square root of 4 minus, although after your last tech assignment, it should be a little easier to visualize some of these things. All right. In this case, you're dealing with something that's definitely some kind of spheroid. It's just a question of whether it's elliptical or otherwise. All right. So we're looking at something along these lines. Now this is only asking us to write the iterated integral. So we'll go with whatever makes the most sense. It gave us everything in terms of x's and y's. So we're in good shape there. But if we had to evaluate that iterated integral, then we might choose to change coordinates. All right. So let me figure out f sub x, which is 1/2 4 minus 4x squared minus 4y squared to the negative 1/2 times negative 8x minus 8y. And f sub y is going to be pretty much the same stuff. Oh, it's sub x. Sorry, my bad. Burp. There we are. F sub y is going to be pretty much the same stuff, except it's going to have a negative 8y at the end. All right. So then it's just cleanup time, get it into our formula for a surface area in 3 dimensions. All right, so we'll do the housekeeping first. I'm just going to move this around a little bit. So the 2 is going to go into the 8 4 times. So it's this one. So negative 4x up top. On the bottom, we're going to have a radical 4 minus 4x squared minus 4y squared. Same stuff, just with a y for the first order partial with respect to y. All right, so my double integral. Now the constraints for x and y, and also z, it's saying it's above 1/2 for z, right? So we got the little bit of an issue there. Really not a terrible issue, but it's something that needs to be accounted for, right? But that's actually going to kind of work itself out in the sense that we're just going to subtract in order to account for that, right? So what we'll do is we'll go from 0 up, and then work our way out from there. All right. Now, when it says x is less than or equal to 0, y is less than or equal to 0, we're talking about everything in the 3rd quadrant. All right. However, this bad boy is symmetrical. So whatever's in the 3rd quadrant is going to be the same as in the 1st quadrant. So I'm going to make an executive decision and say, well, I don't want to work with values that are less than or equal to 0. I want to work with values that are greater than or equal to 0. All right, so this is the same as x greater than or equal to 0, y greater than or equal to 0 due to symmetry. All right, now in my double integral, I'm going to need to account for bounds. These aren't rectangular bounds, so I have to define that in the xy plane. All right, so I'm going to take my original function and set it equal to 0. So I need the surface. Keep doing that. Surface in the xy plane. Zero equals the square root. For, I'll just snag it instead of rewriting it. Snag it from here. Square both sides. We're talking 0 equals 4 minus 4x squared minus 4y squared. Divide everything by 4, move some things around, you're going to get x squared plus y squared is equal to 1. Now, if I want to continue working in rectangular coordinates, bearing in mind that I'm just on the hook for writing the integral or iterated integral. I'm not on the hook for actually evaluating it. Right? Write an iterated integral. So I can live with rectangular coordinates if I want. Right. So if that's what I want, I only care about the top half I'm sorry, if I'm looking at, and I'll just do it this way. If I'm looking down on the XY plane, I only care about, it's the first octant, but really it's the first quadrant in the XY plane. I only care about y equals the square root of 1 minus x squared. So the y values would go from 0 to the square root of 1 minus x squared, and the x values would go from 0 to 1. Right? And then in my integral, as the integrand, I would just have to fit all this stuff in there. Right? So it involves reducing the size substantially, but I can get it in there. So this squared plus same thing again squared just with a y instead of the x plus a 1 I'll have to extend my radical here in a sec. Dy dx. All right. So that goes from the xy plane all the way up. All right. So another way to handle this would, so there's two ways to go from here. One way would be to kind of backtrack and say, well, what if we didn't want to go to the xy plane? You know, what if we wanted to go to the plane where z is equal to 1/2 and up from there? You know, we could do that, or we could subtract off the surface area going from 0, the xy plane, to the plane where z is equal to 1/2. All right. So, you know, it's a separate series of computations. I'm going to reduce the size here, but that, for most people, in my experience, it just seems to be the way they tend to go with this. You know, it's two separate things, but you can go either way. Right. So if you look at the surface in the plane where z is equal to 1/2, I would take the original multivariable function, set it equal to 1/2, square both sides, and use this to isolate something, you know, like whatever makes sense. You know, in this case, I'd have to do a fair amount of side work, but, you know, nothing too crazy. But I would be subtracting, you know, a quarter of 0.25 minus 4, so negative 3.75. That's 15 over 4 negated. Right? So we're looking at 4x squared plus 4y squared is equal to 15 over 4 if we appropriately negate everything. And so we'd have x squared plus y squared is equal to 15 over 16. All right. So then what I would be looking for is the surface area that's bounded between the xy plane and just that far up along the multivariable function, right? So, you know, it's definitely not fun, but it's doable, right? So, you know, that's what we would do in terms of the lower bound. You know, instead of going from 0, where are you? Instead of going from 0 to 1, we would go from 15/16 to 1 and then subtract that off. All right. So yeah, that's just another way of handling it. Actually, it would be from 0 to 15/16 and then subtract it off. All right. So I'm gonna have to resize again. So we solve this for y. Would be equal to 15, instead of 1 minus, it would be 15/16 minus x squared under the radical. So that would be my new upper bound. Make that a little thinner. Right. And instead of going from 0 to 1, I'd have to go from, I think I said 15/16 before I meant the square root of 15/16. Right. So, because there would be the domain associated with this expression. So you can say 15/16 or 15/4, and then subtract the two. All right. So it'd be and subtract. Okay, so you could do it that way. Or if you combine them all in one shot, what you could do is say that you're going from the radical 15/16 minus x squared to the radical 1 minus x squared, and then in turn you're going from radical 15/16 to 1. Right? And that gets you the two respective pieces. Okay, either way is fine. But obviously, no matter how you slice it, this one's got some teeth to it. Right? So again, I try to balance. And then number 10 is a transformation question. So parallelogram ABCD in the XY plane with these vertices. So let me plot those so we can see them. So we'll have 1, 2. Get a label on there. 3, 4. 6, 5. And 4, 3. Okay. So definitely a parallelogram. Now, what we want to do here is transform based off of this relationship that's given. All right. Now they tell us that x is equal to -3/2 u plus 1/2 v, and y is equal to -1/2 u plus 1/2 v. All right. So from there, we could figure out partials and get the Jacobian, but the issue that we're going to run into here is that we need the bounds. All right. So, you know, we could do things simultaneously if we want, but we do need the bounds in order to be able to pull this off. All right. So what I like to do, as you've seen many times, is use sliders. So I'll use u and v. bring this down. And then, so that'll be the x. And the y would be -1/2, -1/2 u plus 1/2 v. And so now I can just kind of toggle back and forth based off of the given u and, well, the u and v values. But the issue is we're in the xy plane. It just occurred to me that we're in the xy plane. All right, so we got some work to do because we need to transition this into the uv plane. All right, so what we're going to do is solve. So I just gave you a little tutorial on how to create sliders. We got some other stuff to do first. All right, so double everything. 2x is equal to -3u plus v. 2y is equal to -u plus v. All right, so what I need is a relationship that's going to solve for u and v given x and y. So they gave us the transformation one way, we need the transformation the other way. All right, so that's kind of aggravating, but it is what it is. All right, so pull this over here. What we can do is use some elimination to help us get that relationship. Let me grab this and this. And I'm going to multiply my second equation by a -1. So we're looking at 2x equals -3u plus v, and -2y is equal to +u minus v. When you add your two equations together, we have 2x minus 2y is equal to 2v. I'm sorry, 2u. In which case x minus y is equal to u. All right, so that's one relation. All right, and that'll help us come up with the other. All I'd have to do is just grab one of them and go from there. So I'll take the 2y and swap out the u for an x minus y. So 2y is equal to -x minus y plus v. So 2y is equal to -x plus y plus v, in which case v is going to be equal to 3y plus x. I'm sorry, it's going to be y plus x. All right, so x plus y. All right, so that actually kind of worked out nicely. I mean, we've only done like the equivalent of Algebra 1 so far, but it's still something. All right, so we got all this stuff and all this stuff to help us get at least started here, which is good because this is actually, like I said, going to be a little bit nicer when it comes to helping us do our transformations, because I want u's and v's. I now know that a transformation giving us u's and v's can now be represented as the u is x minus y, the v is x plus y. All right, so let me just make the appropriate adjustments here. We use the a's and b's. So a minus b. I mean, honestly, you can do it a couple of different ways. I mean, you can do it as ordered pairs, a minus b. Using sliders, it'll just actually populate the coordinates for you, a plus b. So now when I want to create the transformation, if I'm evaluating when, you know, the coordinate is 1, 2, the x value is 1, the y value is 2, right? I now have a transform coordinate, which is -1, 3. 3, 4. I mean, it's easy enough to do by hand also, obviously. I'm just showing you how, like, if the numbers were kind of funky, you could do it on Desmos, right? Because it's just a matter of saying, okay, I'll move this to 3. And I'll move this to, what was it, 4. Right, you get -1, 7. Right. But like I said, it's just a matter of, you know, once you find the relationship, you're subtracting, you know, the x minus the y, so 1, the x plus the y, so 11. The 4 minus the 3 is a 1. The 4 plus the 3 is a 7. Right. So you can see here, hopefully, that you have x values that are going from -1 to +1. And the y values, well, we got that 11 there. It's kind of makes it look funky, but it definitely has a rectangular parallelogram-y kind of look to it. Right? So you can go through that, you know, now that we have all this accounted for, I can start getting rid of stuff because it gets a little crazy. We'll just turn these off so it, you know, they're still there, but I don't have to look at them. So you can look at the new coordinates that are in the UV coordinate system. I'm just checking, sorry, just had a brain cramp there for a second. -1, 7. -111. And 1, 7. All right, so it's definitely parallelogram-like, but now at least we have some verticals in play here. All right, so we have that. We also have linear relationships between the x and y variables. I'm sorry, the x, y, and the UV variables, which is good. So we'll need that. All right, that's for the Jacobian. So I can say that u is equal to x minus y, v is equal to x plus y. So then if I want my Jacobian function, it's going to be the first order partial with respect to x, which is going to give me 1s, with respect to y's, which is going to give me -1s. If I find the determinant of the Jacobian matrix, which would be the Jacobian itself, diagonal down minus diagonal up, so -1 minus -1 gives you a result of 0. All right, so that's a problem. There's got to be a screw up in here somewhere. With respect to x, with respect to y, with respect to x, with respect to y. And we'll come back to that part of it in a second because I'm missing something. But anyway, we would need to come up with a area model because that's what we're looking for. We have area, but transforming that to volume, we need to at least account for the area in the XY plane bounded by that parallelogram or parallelogram. So what we would do is write the equation of lines, all four lines that would pass through these coordinates. All right. So a couple of them are going to be pretty easy. You'd have x equals -1, x equals +1. All right. Then you would also have y equals, I'd have to write the equation of the line passing through -1, 3 and 1, 7. So the slope there would be 4 over 1 minus -1 is 2, so slope of 2. But you could also count boxes, rise over run. All right, so y equals 2 times x minus 1 plus 7. 2x minus 2 plus 7 is 2x plus 5. And that's just assuming that you wanted to do it manually rather than crunching it out. I'm sorry, rather than just looking on the graph. Because it is pretty easy to see on the graph what these equations would be. Because you can actually see where the y-intercept would be for each of them. Right? So if you're going from -1,7 to 111, you'd have to go through 0,9 to get there. Right? So you can kind of just pull it right off the graph too. Right? So from -1,7 to 111, the equation would be y equals 2x plus 9. All right, so these are our boundary functions. You know, it's not rectangular like it's been in some of the other cases, not even triangular, but it's enough to get us some clean values. And I just realized belatedly, because it's very hard to keep some of this straight, these are u's and v's. Right, because we converted this over from the XY coordinate system to the UV coordinate system. So every X becomes the U and every Y becomes the V. All right. So then it becomes a matter so then it becomes a matter of writing the volume equation based off of these bounds. Right. So the double integral, if we're going inner integral is related to U, we know that the U's are going from -1 to 1. So that's C and D. The E, that's actually probably the easiest part because we're finding the volume bounded between Z equals 1 and the XY UV plane, regardless if it's two-dimensional plane with height equal to 0. That would represent the XY or the UV plane. Z equals 1 is a constant. There's nowhere to substitute in for an X and Y and replace it with a UV. So the integrand is still going to be a 1, regardless of what coordinate system you're working with. All right. It's only if it's variable. You know, if you had something like Z equals X squared plus Y to the third or something like that, then you'd have to make some substitutions, but that's not the case here. Right. The bounds for the AB, and this is only because we're forced down this road based off of the nature of the situation, we would say is going from 2U plus 5 to 2U plus 9. But if we were actually supposed to evaluate this, then what we would need to do is reverse the order of integration and go from there. But the one thing that we're kind of hung up on here is the Jacobian. So what we can actually do is go back, because we're kind of suspicious about that E. because it's 1 based off of this, but what's the correction factor based off of the Jacobian? We don't know that, right? Because this came out to a 0. And unless I screwed something up, and I don't think I did, I'm just doing a quick double check. It just zeroed out. No, I did screw something up. I did. I found it. This should have been a positive. I don't know why I made it negative. So diagonal down is positive 1. 1 plus 1 is 2. All right, so it was only a matter of time. But what I would have done, because if I can't get it one way, what I do is I go the other way, and I find the Jacobian of the x in terms of y, and then just take the reciprocal. And that gets the job done too. All right, but what that means is that this is the correction factor, the multiplier for e. So that 1 is actually going to be a 1 times 2, which is 2. All right. Now, because we don't have to evaluate this, we can leave it as is. But if we did have to evaluate it, then what I would do is I would switch the order of integration and redefine things so that it was in terms of b first, and then u. All right. But this is the way it was set up, and that's all there is to it. All right. So let me stop the recording.